Hi folks, Mr. Marshall. I'm going to go through the work and energy slide decks. This is a new unit that we are going to be starting, so slightly new content. And for those that don't know, that's Roger Clemens out there. He's doing work on a baseball. Hopefully you guys took a look at the reading yesterday for our science definition of work. Work has to accomplish something, so it's different than just applying a force to a stationary wall. You can do that all day, you'll be tired, but you'll accomplish nothing. If you apply that force and move the wall, then, only then have you done work. Our topics today, I'm going to talk just about work and we'll get up to potential energy. This idea of conservative and non-conservative forces is really important in the real world because sometimes you do work and that work basically gets stored as energy and you can get that work back out. Some work gets lost and it basically just turns into heat and is absorbed by our surroundings. So when you push a chair across the floor, you did work on it. That's a non-conservative force because the friction that you overcame turned into heat and all that work is gone. On the other hand, if you take a book and you lift it up, you did work lifting it, but that work gets stored in something called potential energy. If you let go, that book will then fall back down. So the energy that you stored lifting the book can then be released and turned into the speed of the book falling. So this should be right about what the book was explaining to you that I assigned yesterday. So work is when you apply a force over some kind of a distance. The force is going to be in newtons and the distance is going to be in meters. And that's important because when we measure work, it's going to be in Newton meters, and it's such an important concept in physics that we gave it a name. The Newton meter is known as the joule. And I seem to have a face here that's over. Okay. This also applies to pound feet, but pound feet in units of work is not equal to a joule. 1 Newton meter is a joule, but a foot pound is not. For that reason, we don't use foot pounds. And we're going to talk about how important joules is for connecting different types of work and types of energy as we move forward. So far it's a simple multiplication and it's an absolute value. When you do work, you do work. It's not going to be positive or negative. And when I say that, you can subtract work, but that work itself is a scalar value, meaning it doesn't have a positive or negative. When you subtract it, you remove work from the system, but that doesn't mean that it's negative. It's a scalar value that you're removing from the system. The other piece to this is that the force that you're applying and the displacement have to be in the same direction. That being said, if you're trying to lift up a pickup truck and it drives forward, you did not do that work. The work that you're doing is in the same direction. In this picture, the woman pulling the crate is applying a force. Force is a vector. The direction of that force is twofold. It's going both up and to the right. The crate is only moving to the right. So all the force that she's applying lifting the crate up, and we can trigonometry and figure out how much force is lifting the crate up, that force is not doing any work because the crate is not moving up. It's only moving to the right. So when we figure out how much work is done, we have to figure out how much of the vector force, vector meaning the force that she's pulling up and to the right, how much of that vector force is being applied in the going to the right direction. So trigonometry, the going to the right direction is the adjacent side of that triangle, so we want the cosine value of the force. Here's a quick problem that we would ordinarily do in class. The important pieces of this are that kilograms is not a force. Newtons are a force. So how much work does it take to get a 1,000-kilogram roller coaster up a 12-meter run? So usually the roller coasters work like this. The roller coaster is going up and at an angle, but we only care about this part. It's going up 12 meters, and the amount of force it takes to lift 1,000 kilograms is 1,000 times 9.8. So I'm drawing with my finger. It's the best I can do. I'm going to repost this in a forms. So you're going to come up with the weight in newtons times the distance that it comes up with, and all that work that it takes turns into something called potential energy that we're going to start to talk about next. As that potential, as it starts to go downhill, the potential energy, stored energy, turns into kinetic energy, and kinetic means moving, like kinetic friction. That term means moving friction. Kinetic energy means moving energy. So here's our joules. This becomes really important. The joule becomes really important because we're going to start to talk about electric work. We're going to start to talk about fluid work. And when we do that, electrical work is measured in volt coulombs. And if you do a lot of dimensional analysis, it turns back into Newton meters, but we simply call electrical work joules as well. So, oh, nope. Well, another point to be made here is that this work that's being done, not all forces do work. So gravity will do work. Anything you drop, gravity will do work as it applies a force on a distance. But in the case of the force of gravity acting on the moon is being attracted towards the Earth. However, the moon is not coming towards the Earth. So even though it's applying an enormous force on the moon, since the moon is not moving towards us, since that displacement is not heading towards Earth, gravity is doing no work in this case. Work is force times distance. The force is towards Earth, the distance is 0. So that equates to 0 work. Okay, so work and energy, I've talked about potential and kinetic energy. It's annoyingly circular, but we'll get around that. We're going to learn that when you do work, you're giving an object energy. When you're exerting energy on an object, you're doing work. So energy is the ability to do work. When you give something potential energy, you're applying a force over a distance. When you do work, you increase an object's energy, like when you lift an object up and give it potential energy. If you hit a hockey puck, you do work, you apply a force over some period of distance, then that hockey puck starts moving. That motion is kinetic energy. Let me hide my face in case that's not all forces are able to do work, like that centripetal force example. So this is what I thought we were getting at before. AA battery, an alkali battery, contains 1,750 joules of energy. That's an approximately correct value. If a 100% efficient motor was attached, how far could it lift a 2-kilogram textbook? So this is an important one because it's saying work equals force times distance. What we need to realize is that the potential energy of that battery, that's how much work that battery can potentially do. I apologize for the writing. It's over 30% worse than my normal writing, but this is kind of what's happening here. So this is how much work that battery can do in joules, which means it can move a 2-kilogram textbook. And remember, newtons is a force, not kilograms. So we're doing 2 times 9.8, which is 19.6, times whatever that displacement vector is. If you're lifting it, then the distance has to be in the same direction as the force, and that'll be work. I'll put this in a force at the end too. Here is where we start talking about that potential energy. And whenever I give you a mass, I'm multiplying by 9.8, that acceleration of gravity, to turn it into a force. So work is force times distance, but you have to realize that when you're lifting an object, that force is the weight. When you lift an object, the force that it takes is the weight, and the weight of an object is mass times gravity. Potential energy refers specifically to lifting an object against gravity. So when you give an object potential energy, you're lifting its mass against gravity, 9.8, some height, which is measured in meters in the water. So this question is basically saying, how much work does it take to lift up this skater? It's the same as the roller coaster, but they're just saying how much potential energy does a 100-kilogram skater have before she starts her ride 12 meters above the ground. It's the same as a roller coaster that's 12 meters. The work needed to lift this person is the same amount of potential energy that the person has. So if you do 12 times 100 times 9 Newton meters of work, you'll give it 12 times 100 times 9.8 Newton meters or joules worth of energy. So this is the third question that I'll put in the forms. And we'll end with the idea of kinetic energy, and then we'll tie kinetic energy in probably next week a little bit more. With kinetic energy, when you do work to an object, you can give it potential energy if you lift it up. If you're pushing it, you can also give it kinetic energy to make it move. So when you apply a force over a distance, like you hit your gas pedal over 100 meters, your engine applies a force over that distance, it's going to increase the speed of your car. And speed of your car is kinetic energy. The equation for kinetic energy is, I guess, a little harder. What's going to be hard is when we start rearranging it to solve for velocity, but that'll be next week. We're basically taking energy and we're going to figure out how fast we can make an object go. We know some things from our forces unit that the more mass it has, the less velocity it's going to have. So the difference between pushing a bus and pushing a skateboard is going to be significant. When you put a small engine in a Yaris, it goes just fine. When you put a small engine in a bus, it doesn't, because the amount of force is the same. If there's more mass, you're going to get less velocity off of that force. So in that way, kinetic energy is going to start to look familiar with some of those ideas. In this case, we're going to include the fact that you're applying that force from the engine over a distance. And the longer you apply that force, the more energy you're going to give that vehicle. So we're going to pick up on kinetic energy next time. Take a look at the couple problems in the forums for me. It's my daughter's room.